So graphs are very important. Many things can be represented by graphs, like a network diagram or relations among your friends, things like that. For more details, you need to watch the lecture video, of course. So 8.5, representation of graphs. So by definition, a graph is just a set of graph consists of two sets, V and E. That is a graph, and I just represent the graph using a diagram like this. But there is another way of representing graph, also very useful. And so let's say we have a graph G, V, comma, E. It says graph with V, V1, V2. Let's say we have n vertices like that. So the vertex set is this, V1, V2, dot, 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 Vn. And the adjacency matrix of G is the n by n matrix A. So it's Aij. What is the Ij entry? So n by n, so it's I and j are from 1 to n. Where, what is Aij? It's a number, integer, or it's just the number of edges between. So this is not necessarily a simple graph. There may be loops and multiple edges. So number of edges, there could be more than one edge, Vi and Vj. In other words, we can think of this matrix whose rows and columns are indexed by the vertices. And of course, here we have to specify the ordering of the vertices, because if you write down the matrix, you have to specify which is the first row, the second row, etc. So it is assumed that we have this ordering V1, V2, etc. Okay? So example. Suppose that we have a graph which is represented by this diagram. This is not a simple graph. It's like this. So B, A, C, D, and E. So we have a graph like this. So what is the adjacency matrix? Where we order the vertices like A, B, C, D, E. So it's a matrix, 5 by 5 matrix. And think of the rows indexed by the vertices. So A, B, C, D, E. And A, B, C, D, E. Okay? And for each entry here, write down the number of edges between the two vertices. What is the number of edges between A and A? Meaning the loops at A. There is no loop, so 0. Right? And number of edges between A and B, there is only one edge, so write down 1 there. Number of edges between A and C, also 1. A and D, we have 1, 2, 3. So here we put 3 there. Number of edges between A and E, there's no edge, so 0. Etc. So you can complete the matrix. B and A is 1, there is 1. And BB, there is a 1 loop at B, so it's going to be 1. Number of edges between B and C, 1. And it's not connected to anything else directly, so 0, 0. And C is connected to A by 1 edge, B by 1 edge, C no loop, D 2, nothing between C and E, like that. E and A, there are 3 edges. E and B, nothing. D and C, 2. D and D, nothing. D and E, 1 edge. E is only connected to D by one edge, so it's 1 and zeros elsewhere. Okay? This is the adjacency matrix. And of course, if you give a different ordering of the vertices, you get a different matrix. But the matrix is just the matrix obtained by permuting rows or columns. Okay. Using the different ordering, you will get a different matrix, but they are somehow related. Okay, so this is not a simple graph, but if you look at this graph at the adjacency matrix, can you tell immediately whether the graph is simple or not? So suppose that you don't know this, you haven't seen this graph yet. You are only given this adjacency matrix. Can you say that this is a simple graph or not? What is the criterion for the simple graph? We must have zeros and ones, right? Only 1 or 0. Every entry must be 1 or 2. Because 2 or more means we have multiple edges. And also, the diagonal entries must be all 0. Because diagonal entries are the number of loops. So, for simple graph, it's a 0-1 matrix. If G is a simple graph, then A is a 0-1 matrix, meaning every entry is 0 or 1 matrix with diagonal entry 0. 0 diagonal entries. Diagonal entries must be 0. So, in fact, ij entry is what? Is either 1 or 0, right? Because it's a 0-1 matrix. 1 if the ith vertex and jth vertex are connected by an edge. Otherwise. So it's simpler. 1 or 0, 1 if they're connected by an edge, 0 otherwise. Let's see an example. And so what is this? What's the good thing about this matrix, adjacency matrix? One thing is it is a kind of a compact way of storing a graph, right? This is good. This is good one because we can visualize the graph. But if you suppose that you want to store this graph, you want to kind of make some code so that computer can do something for you. So maybe for computer, this is not very effective for computer to memorize. But this one is just an array of numbers, so which is very simple for computers. So if you use computer, maybe this kind of matrix array of numbers can be useful to store your graph in a computer. That's one thing, one useful thing about this adjacency matrix. But there is more. Also an interesting property of the adjacency matrix. Suppose that we have a graph G that looks like this. A, B, C, D. What's the adjacency matrix? So it's a 0-1 matrix because it's a simple graph. A, B, C, D, and A, B, C, D. I'm just write down the matrix. 1, 1, 0, 1, 1, 0, 1, 0. You can see that's a 0 matrix. By the way, it must be a symmetric matrix, right? Because if there is an edge between I and J, obviously there is an edge between J and I. Sometimes we consider directed graph where we have the directed pair from I to J. We distinguish edge from I to J and J to I, but not here. We will not consider directed edge just yet. Because the edges are unordered pairs of vertices. It must be a symmetric matrix. Simple or not, it must be a symmetric. So it's a matrix, so you can consider multiplication of the matrix, or square of it. Let's compute A squared as a matrix. So So let me copy the matrix over here just to compute the matrix square. So when we multiply two matrices, we do as follows. Let's see, we want to compute the two 4 entries, so it's B and B. Oh, yeah, you know how to compute this. So let me write down the result. It is like this. And we're going to focus on one entry. 1, 2, 1, 2. Okay, everyone knows how to multiply two matrices. So let's focus on this entry, B, comma D, in this square matrix, A squared. How do we compute this? How can we compute this? Basically, we take the dot product of this vector and this vector, right? Dot product means you multiply the corresponding entries and then add the result. So 1 times 1. So in other words, this 2 is obtained like this. 2 equals 1 times 1 plus 0 times 0 plus 1 times 1 plus 0 times 0. Okay? This is 2. This is how we multiply 2. But from here, so what does that mean? So 1 times 1 is 1, plus 0 plus 1 plus 0, very simple. 1 plus 1 equals 2, that's why it's 2. But, so here, if you look at every term carefully, we get 1 or 0, right? Because we multiply 0 or 1. If you multiply both 1 and 1, then we will get 1. Otherwise, we will get 0. 0 times 1 or 1 times 0 or 0 times 0, we will get 0. So the result here will be the number of ones after multiplication. But when do we get 1? This, if both this and this are 1. Only in that case we obtain 1, right? So here, if you look at this, we get 1 and 1 at the same position. First entry in this row, first entry in this column. What does that mean? This corresponds to matrix, this corresponds to A vertex, this corresponds to A vertex, right? This means B and A are connected by an edge, like this. And what does this mean? A and D are connected by an edge. Only in this case, we add 1. So we add 1 if we can go from B to A by an edge and A to D by an edge, right? This is 1. What about this? So here we got another 1, and that corresponds to this entry and this entry. This corresponds to C, this corresponds to C, and here you can see B is connected to C, and C is connected to D. So whenever you can go from B to D by visiting one vertex, like one vertex and then to D, then that corresponds to one term over here. In other words, the entry here, 2, is the number of paths from B to D of length 2. Length 2 means we use 2 edges. Like over here, this is a path from B to D using 2 edges, 1 and 2, and 1 and 2. As you can see, there are only 2 ways of doing that, right? And that's the number over here. It's not a coincidence. It's true for every entry. So for instance, let's look at this part. This means there are 3 ways to go from A to A by visiting one more vertex, or by using a path of length 2. How can you do that? Here you can go this way, or this way, this and this, and this and this. There are 3 ways of going from A to A. by visiting one vertex. Okay? Does this make sense? Let me summarize this as a theorem. So we can state the theorem as follows. So G is a graph. Not necessarily a simple graph. Maybe may have multiple edges. So A are the adjacency matrix of G. And let's say K is an integer greater than or equal to 1, positive integer. Then the ij entry of kth power of a to the k, is the number of paths from, let's say, path of length k from the ith vertex to the jth vertex. So in the previous example we saw k equals 2k, but in general it's true. Okay. Let me prove this. Proof is not difficult. We will prove this by induction on n, on k. So k equals 1, what happens? If k equals 1, is this true? That's true by definition. It's true. Because A is the adjacency matrix. Aij means number of edges between Vi and Vj. Number of edges is exactly the ij entry in the adjacency matrix, so it's true by definition. So suppose it's true, the base step is done. Suppose that is true for k and consider k plus 1. So what is ak plus 1? But this is the matrix k plus first power of a, so it's ak times a to the k times a. So what is the ij entry over here? So we want to show that it's also true for k plus 1 case. So here ij entry of the matrix, ij entry. So this is a product, a multiple of two matrices. So this is like summation L from 1 to L. So here we take IL entry. From the first matrix we take IL entry. The second matrix we take LJ entry. This is how we multiply two matrices. The IJ entry is computed like that. If you want, I can draw the diagram of the matrix. So it's okay, I think I need to. So this is equal to this times this matrix multiplication, a to the k, a. And the ij entry, if this is I and this is j, the ij entry here, this is obtained by taking the dot product of ith row of the first matrix and jth column of the second matrix, right? So we multiply this and this and this and this, and then you add them. This is how we multiply two matrices. All right, but what is this number? The IL entry of the matrix. And this is power of A, and A to the K. And by induction hypothesis, this is equal to number of path of length K from where to where? Ith vertex to lth vertex. Okay? What about this? This part. This part is equal to number of, it's edge or path. Let's say edge. from, we don't have the direction, but let's say from VL to VJ. Or edges between these. Okay. I think I need more space, so I'm going to continue in the next page. So eventually we will conclude that this number, the sum of these numbers, must be equal to the number of paths from ith vertex to jth vertex of length k plus 1. But that is not difficult because suppose that we have we have two vertices, Vi and Vj. Every path of length k plus 1, we must first use the path of length k and then one edge, right? Every path, if you look at the last edge, we must have this decomposition, like path of length k plus one edge. So it's a path, this part. This is a path of length k, and this part is an edge, right? Every path of length k plus 1 from Vi to Vj is obtained by combining first a path from path of length k from Vi to VL for any for some vertex L, and an edge from VL to Vj for some L, VL, right? For some vertex VL. Everything is obtained this way, right? And VL can be anything. So we just sum over all L from 1 to L. That means this path, number of such paths, is the sum, L from 1 to L. This number times this number, but we know that this number is AKIL, ALJ, which is exactly a k plus first power ij. So this is the proof. This is the proof of the inductive step. So it's done by induction. So that's the end of the proof. So if you look at the algorithm, how we compute the multiplication of two matrices or more, that's exactly the same as we go from one vertex to another, etc. So this is a useful theorem. You can compute the number of paths from one vertex to another of length, given length, by just computing the power of a matrix. So especially very easy to program this using computer. Okay. And so this is the proof. So there's another way of representing a graph. It's called using incidence matrix. So V, comma E. So V is set of edge vertices, V1, just V1 to Vn. And E is a set of edges, and let's say the edges there are m edges like this. And of course, each EI is a pair of two vertices there. And the incidence matrix of G is the matrix. So n by m matrix, basically m Mij, where I is from 1 to n, j is from 1 to m. So it's n by m matrix where Mij is, this is always 1 or 0. 1 if Vi is incident to Ej and 0 otherwise. A vertex is incident to an edge, that means this edge contains that vertex. So it's best to describe this using an example. So G may not be a simple graph, but it's okay. So V1, V2, V3, V4, V5, and we have edges like this. Let me label the edges like this. E1, this edge is E1, this edge is E2, E3, and this loop is E4, and this edge is E5. I think it's a little confusing, so this is E2, E5, E6, and E7. Then the incidency matrix. So the rows are labeled by the vertices. So it's V1, V2, V3, V4, V5. And the columns are labeled by the edges. So it's E1, E2, E3, E4, E5, E6, E7. So here you place 1 if V1 is one of the endpoints of E1. V1, it is incident to E1, so we put 1 there. Actually, you can write, just focus on each column. So E1, the 2 endpoints are V1 and V4, so you put 1 there, V1 and V4. So every column must have 2 1s and 0s elsewhere. And what about E2? The 2 endpoints are V1 and V3, so we put 1 and 1 there. And E3, 2 endpoints are V1 and E1. Where are they? V1 and V2, like that. And E4 is V2, but we press only 1 there, so if it's a loop, we have only 1 1. E5, V3, V4, E6, 3 and 4, the same. E7, 4 and 5, like that. And zeros elsewhere, like 0, 0, 0, you know. So in this incidency matrix, you can see which vertices are endpoints of an edge, etc. So sometimes people represent graphs using incidence matrix, but I think adjacency matrices are more common to use. But it's also possible to represent like that. Any question? Okay, then let's move on to the next page, next part. 8.6, isomorphism of graphs. So this is in fact an important concept. The main question is, how do we distinguish graphs? So graphs are just pairs of sets, vertex set and edge set. How do we say that these two graphs are the same or these two graphs are different? So for example, suppose that we have a graph like this, vertices are 1, 2, 3, 4, 5, and edges are like this. And another graph is like this. Also 5 edges, 5 vertices, 1, 2, 3, 4, 5, and 5 edges. These are not vertices, only 5 edges and 5 vertices. So we have one graph on one side, on the left, another graph on the right. Are they the same graphs or they are different graphs? How do you think? Are they the same or different? You know, just by using the definition, graph here in this case, it consists of two sets, V and E. What is V? 1, 2, 3, 4, 5. We don't really care about the drawing of this graph. We only focus on the abstract sets, V and E. So what is E? 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, 4 is connected to 5, and 5 is connected to 1. The ordering doesn't matter, so it's fine if you write 1 and 5, 1, 5. Let's say this is G and this is H. What about H? V is A prime, E prime. But you can see V prime is exactly the same as this. 1, 2, 3, 4, 5. What about E prime? 1, 2, 2, 3, 3, 4, etc. So in this case, they are really exactly the same graph, exactly the same set of vertices, exactly the same set of edges. So even though I draw them in a slightly different ways, but they really are the same graph. Do you agree? Right, just by using the definition. So in this case, it's not that bad. It's quite simple, but let's see another example. One, 2, 3, 4, 5. So you have the same graph G. Now let's say H is now this. A, B, C, D, E. So here I use numbers 1, 2, 3, 4, 5. Here I use alphabet A, B, C, D, E. Are they the same graph or not? You know, here the vertex set is 1, 2, 3, 4, 5 as before. But here the vertex set A, B, C, D, E. Obviously they are different. 1, 2, 3, 4, 5, they are different from A, B, C, D, E. So they are different graphs, right? So they are different graphs if you just use the definition. But are you satisfied with this distinction? They are different graphs, period. What would you say? Do you think they are really different, or their vertices are labeled different letters? But you know, these labelings, this is not what we really care. The thing is the structure of this graph. You know, they look the same, exactly the same. They have exactly the same shape. So we want to say that they are, in some sense, the same graph, even though their labels are different. We want to introduce some kind of concept so that we can say that they are the same graph. So this is basically equivalence relation. So in other words, we want to give some kind of equivalence relation on the huge set of graphs, so that these two are equivalent under that relation. We want to give a nice relation among these graphs, so that it's really an equivalence relation, and then under that relation they are equivalent. We want to say, or we want to introduce that kind of notion. And the notion is as follows. Let's do it in the next page. So the definition. G1 is V1, E1, G2, V2, E2. let's say these are simple graphs. We can do this for non-simple graphs, but just for simplicity, as the name suggests. Let's consider simple graphs. It's simple. We say that these are isomorphic. G1 and G2 are isomorphic if isomorphic basically means they are somehow of the same shape in some sense. If there is a one-to-one onto, so bijection, in other words, bijection from one vertex set to another such that if there is an edge between u and v, this is if and only if the f of u and f of v are in the edge in the other set. Yeah, the definition is looks a little abstract, so we need an example. But the definition is like that. Then if there is a bijection from one vertex set to another, if there is an edge here, then there must be an edge on this image. So if you have two vertices u and v, if you follow this map f bijection, then you have two vertices on the other graph, and they must be connected by an edge, if and only if the original uv are connected by an edge over here. So if you think about this a little bit, you can see this. If this happens, then they must be looking exactly the same way. So example, in this case we usually write something like this. G1, this means isomorphic. Like they're not quite the same, but they look the same, isomorphic. So example, we have this graph. 1, 2, 3, 4. And this is isomorphic to this graph. A, B, C, D. They are not exactly the same graph as graphs, but they are isomorphic. Suppose that, but why? Why are they isomorphic? To show that two graphs are isomorphic, you need to find the bijection f from one vertex set to another. So in other words, you have to make a correspondence between the vertices. So one corresponds to some vertex here, 2 corresponds to some vertex there, etc. How do you want to make the correspondence? So F1, what do you want to say about this? F1. In order to find the isomorphism, you have to look at the graphs carefully. You can see this 4 is kind of special. It's only the vertex of degree 1. Degree means the number of edges incident to that vertex. And you can see the degree of B is the only vertex of degree 1. So maybe F1, F2, we will have to define F3, F4. But this F4 must be the vertex B, right? If they have the same, they look the same. And you know, 4 is a special vertex in that way, but 3 is also special because that's the only vertex connected to 4, right? So this must be the vertex connected to B over here. So you can see 3 must be A, right? What about A and 1 and 2? Doesn't matter. Let's say A is C and B is D, but it's okay if you say D and C. You will see. Then this is an isomorphism. In this case, this is called the isomorphism. But why? Why is this true? Why is this an isomorphism? So F is called isomorphism. Why is F an isomorphism? For every two vertices, say, for instance, 1, 2, consider this. 1, 2 is in an edge, is in the edge set, right? E1, say. And what are the images of this? F1 equals C, F2 equals D, CD is also an edge over here, right? For every pair of two vertices, if this is true, then it's not. This is also true. And also, let's say 1 and 4. This is not in E1, and their images F1 equals C, F4 equals B. C and B, they are not connected, so it's not an edge here. For every two vertices, if you consider the pair of them, they are in the edge set if and only if the images are in the edge set. So if you draw this diagram a little differently, so suppose that we could have represented this in a different way. So try to okay, let's write over here. Write this in the same way. 1, 2, 3, and 4, and 1, 2, 3, 4. So write F1, F2, F3, and F4. What is F1? F1 equals C. F2 equals D. F3 equals A. F4 equals B, right? And then C, which of them are connected? Here, just one. A and C are connected. A and B are connected. A and D are connected. If you redraw the diagrams, the graph this way, by arranging the vertices the same way, then you can see they really look the same. And that's basically the idea of the isomorphism of two graphs. So intuitively, you should think that two graphs are isomorphic if only if they look exactly the same, if you draw them like nicely like this. Then they look exactly the same. Only the labelings of the vertices are different. Or if you use adjacency matrix, then you can see the following theorem immediately. G1 and G2, these are isomorphic if and only if, this means if and only if, there are some ordering of V1 and V2 such that their adjacency matrices are equal. For example, I'm using the same example, like let me draw this again. 1, 2, 3, 4. We know that these are isomorphic, A, B, C, D, right? So what is the adjacency matrix of this? So let's use the original order, 1, 2, 3, 4. 1, 2, 3, 4. And you can see 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0. If you use the ordering A, B, C, D, then the two adjacency matrices are different. But if you reorder this, actually the ordering is like F1, F2, F3, F4. What is F1? F1, F2, F3, F4, they are like C, D, A, B. So let's use that ordering, C, D, A, B. C, D, A, B. C and C, the diagonal entries are all zeros, simple graph. C is connected to A and D, so it's, it should be A, right? C, A and D, right? Not to B. D is connected to AC, right? A is connected to all of them except A. B is connected to only A. And you can see they are really the same matrix, exactly the same matrix. And because they are isomorphic. The graphs are isomorphic. And this is an if and only if condition. If you can rearrange the matrix, adjacency matrix, by permuting rows and columns, by changing the ordering of the vertices, and if the matrix, adjacency matrix, is the same as the adjacency matrix of the other graph, then they are isomorphic. It's an if and only if condition. And the map, and you can think of this as a mapping from, this is basically a map F. F1 goes, F sends 1 to C, sends 2 to D, etc. Okay. Right. In this example, we saw the two vertices, two graphs are isomorphic. So suppose that you want to show that two graphs are isomorphic. Like I did over here, you just need to find the bijection, right? Find the bijection, explicit bijection, and then show that, yeah, look at this. They are, the adjacency matrices are the same, or they have this, it is an isomorphism. So let's consider the other example. Suppose that two graphs are not isomorphic. How can we show that? How can we show that two graphs are not isomorphic? If they are isomorphic, you can just find one bijection, isomorphism, but what if they are different? That's the question. Actually, one way, very time-consuming way of doing this is, how many bijections are there from one vertex set to another? If they have the same number of vertices, say n. There are n factorial permutations, right? But bijection must be one-to-one correspondence. So if suppose that G1 is like a V1, comma E1, G2. So here we want to show that G1 is not isomorphic to G2. But most simple-minded proof will be the following. There are, say, like V1 equals V2, there are n vertices. If there are, first of all, if V1, there are like 5 vertices in one vertex, there are, say, 7 vertices in the other vertex, they cannot be isomorphic because you cannot find the bijection from 5 vertex set to 7 vertex set. So suppose that they are the same. There are n factorial bijections, permutations, because basically permutations. Right? Consider all bijections, and then for each bijection, show that it's not an isomorphism. That will prove that they are not isomorphic. But do you think this is a good idea? You can do this, but it will take a lot of time. If we can show that none of these is a bijection, is an isomorphism, we are done. But not a very good proof or efficient proof, because so many things to check. N factorial is a very big number. So we don't want to do this. We need something else. So we need to introduce another concept. Let's say G is a graph. A graph has many properties, many. Some property, a property of G is called an invariant if every graph isomorphic to G also has the property. invariant. Okay, so the definition is not very explicit. If some property satisfies some kind of condition like this, then it's called an invariant. So there are many invariants. There are infinitely many invariants of graphs. So we cannot really list them all. But there are some useful invariants. Let me give you some example. Probably the simplest invariant will be the number of vertices. Number of vertices is an invariant of a graph. Okay, number of vertices is kind of property of a graph. Number of vertices is 5. It's a property of a graph, right? Some graph may satisfy this, or some graph may not satisfy this. You know, some graph may have 5. If it has 5 vertices, it has this property. If some graph has like 10 vertices, it does not have that property, etc. So number of vertices is a property, and it is an invariant. Why? Why is an invariant? So actually, more precisely, the property, say G has n vertices. This property is an invariant because, you know, in the definition, precisely speaking, this number of vertices, that means the G has n vertices, like that. Okay, so why is this an invariant? Because if some graph has this property and another graph is isomorphic to this, this must have the same property, right? Why? Suppose that G has n vertices and G and H are isomorphic. Then what? H also has n vertices. Why? You know, this, let's say V1 and E1, and let's say this is V2 and E2. They are isomorphic. That means because there is a bijection, one-to-one onto map from one vertex set to the other vertex set, right? But there is a bijection. That means they must have the same cardinality. So it's obvious that it's an invariant. Okay? Do you agree? Why is this important? Because suppose that you want to show that two graphs are not isomorphic. All you need to do is to find one invariant such that this graph has that property, but this graph does not have that property. Then they cannot be isomorphic. That's how we prove that two graphs are not isomorphic. So for example, let's say G1 equals this, 1, 2, 3. G2 equals this, 1, 2, 3, 4. Of course, we immediately can see that they are not isomorphic. They cannot be isomorphic. But how can we prove, precisely how can you prove this? G1, the proof goes as follows. G1 and G2 are not isomorphic because number of vertices of G1 is not equal to the number of vertices of G2, right? Because here is 3, this is 4. But we know that number of vertices is an invariant, meaning if they were isomorphic, they have the same number of vertices, because number of vertices is an invariant. So you can immediately say that they are not isomorphic. So another example, G1, 1, 2, 3, G2 is this. Are they isomorphic or not? They are not isomorphic because find one invariant so that G1 satisfies and G2 satisfies, or invariant, different invariant. Number of edges is also an invariant. That's obviously invariant, right? If there is an isomorphism between two graphs, there must be the same number of vertices, and because one edge exactly corresponds to one edge over here, the number of edges is also an invariant. Number of edges equals 2. Here, number of edges equals 3. But number of edges is an invariant. They are different, so not isomorphic. This is a proof. So all you need to do is to find one good invariant. But sometimes it's not. It can be difficult if the graph is complicated. So there are many, many invariants. For example, I think this kind of problem is interesting. It's like a solving puzzle, right? You find something that is here but not there. Or it's like, this famous game, finding different pictures, right? Difference between two seemingly the same pictures. You need to distinguish them. Oh, wait. I didn't want to write this first. Yeah. It's kind of a hint. Okay, so this is not a vertex. So we have 1, 2, 3, 4, 5, 6 vertices here. Also 1, 2, 3, 4, 5, 6 vertices. They are not isomorphic. Why? They have the same number of vertices. What is the number of edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They have the same number of edges. So we cannot conclude yet whether they are isomorphic or not. Right? So we need to find another invariant that distinguishes these two graphs. Number of vertices doesn't work, number of edges doesn't work. So we need to find more sophisticated invariant. Let's consider degrees of the vertices. So degree is number of edges connected to each vertex. So here, the 1, 2, 3, right? Here the degree is 2. Degree is 1, 2, 3, 4. Degree 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. So degrees here are in this decreasing order 4, 4, 4, 3, 3, 2. Okay? What about the degrees over here? Degree is 2, 1, 2, 3, 4. So 4, 4, 4, and 4, and 2. Here the degrees are 4, 4, 4, 4, 2, and 2. They are not the same. But the degrees, the sequence of degree is an invariant. Because they look exactly the same, if there is something over here, the degree must correspond to the same thing. So the sequence of degree sequence is an invariant. But they have different degrees, so they cannot be isomorphic. Okay? There are many, many invariants. But we may ask this question. So in this example, number of vertices was enough, number of edges was enough. Here, degree sequence was enough. But can you have a list of invariants so that all we need to do is to look at these invariants? But that's not that simple. There are many, many invariants, so we cannot really look at just a simple list of invariants. You really look at the graphs carefully and then need to find an invariant in your own. Sometimes it can be kind of complicated. So for example, let me give you an exercise. Like maybe you can do this, try to show that these two graphs are not isomorphic. Both have 8 vertices. You need to find an invariant. And it's like this. It's little edges like this, and here. So try to find as simple invariant as possible that distinguishes the two graphs. Find a property that this has invariant that this graph satisfies, but this does not. Yeah, I'm going to give you maybe 3 minutes. You need to look at many things. If this doesn't work, try to find another, try to use another invariant, etc. Both have 8 vertices. So that's right. Did you find proper invariant distinguishes these two graphs? Can you raise your hand if you found one? Tell me if you found one. No one? Really? Does that mean they are the same graph, isomorphic? No, if no one found an invariant, maybe there is a possibility, but that cannot be a proof, of course. And they are different. I have an invariant. Anyone wants to say? Okay, I will tell you. Probably some of you already know, but invariant is triangle, having a triangle. Having a triangle is a property, right? Some graph may have triangle, some graph may not have triangle, but it is an invariant. If some graph has triangle and something is invariant to this, it must have this triangle because they must have the same shape. For here, it has a triangle. There are many, but there is one triangle, like this, right? But here, you cannot really find the triangle. There is no triangle in this graph. So it is an invariant and proving that they are not isomorphic. So you need to find an invariant like this. Sometimes it can be more complicated. But this kind of a game, puzzle, right? If you think this finding an invariant to distinguish two graphs, if you think this is very strange, then I think you're wrong, because we use this kind of technique in our real life, right? Suppose that there are many examples, but suppose that you distinguish two persons. Like a photo, you have a photo of two persons like that. And you have one picture of one person, another picture of another person, and you don't know whether they are the same person or not. But if you have some kind of invariant, then you can distinguish them. For instance, suppose that this guy is a man and this guy is a woman, then being a man or woman is an invariant for a person, so they have to be the same, they have to be different, or not. They say, nowadays, sometimes people can change the gender, but anyway, invariants are like that. So, we use this kind of technique in our real life, and that's the same for mathematics. So mathematics, the definition looks very abstract, but there is a motivation of doing this, and that is very useful to distinguish, and then it is applicable to real life.